Say we have two molecule. Say this is the molecule 1 and the other one is the molecule 2. Okay, so we here the distance between molecule 1 and molecule 2 is r. Okay, so there must be intermolecular force between these two, these two molecules. Now I'm going to show you a of plot of uh, r along the axis x and electrostatic potential energy along the axis y. Okay, so you see here this I represented. So is the r is the distance between molecules, and here u is the potential energy. So potential energy means we are talking about electrostatics. Electrostatics, the potential energy. Okay, if you plot a graph of these two, we'll see that it follows the pattern of let's see here, pattern of looks like starting from higher value goes down and becomes minimum, and again nearly exponent parallel to the axis x. Okay, so you see that when the separation between atoms is r naught, corresponding to this value r naught. Okay, r naught, the potential energy is the lowest. So we represent this by u naught. Okay, so u naught is the lowest possible value of electrostatics potential energy. So at r equal to r naught, the electrostatics potential energy. Okay, so we represent by u is lowest or minimum. Okay, so this minimum value we call it u naught. Okay, so you see that when you move towards left, means a smaller value of r naught, the potential energy increases sharply. Okay, so let's draw the other plot of force and the r. Okay, so let's see, this is force along the axis y, and the separation between the atoms or molecules is along the axis x. If we plot this, our patterns will be look like this. It's very similar to the potential energy, but you see here that based on the previous plot, we have the lowest possible potential energy is u naught. So let's see here, I started to draw like this. Okay, then it goes like this. So you see here the potential your at distance r naught, same as before. At this point the force value is 0. Okay, so at r equals to r naught, force between the molecules is 0, and at that condition, at that point, the electrostatics potential energy is lowest, or we can call it minimum. Okay, U naught. So the upper portion, this will represent the repulsive nature between two molecules. Okay, so in this case, the value of R is less than R naught. So you see from the picture that at that condition, the value of force is actually greater than 0. If you consider those portion of the graph, this portion is basically represents the attractive nature of the atoms or the molecules, and this is the region where R is greater than R naught. So in that case, the value of force is basically greater than 0, is less than 0. Okay, so this is the scenario it looks like. So in this both the graph, we consider that the gravitational potential energy is very small. Okay, so gravitational potential energy we considered here is negligible. So we know from the previous chapters is that there is a relation between relation between the gravitational potential energy and the force. Okay, so I write, remember, you have to remember like this from previous chapters, we have the relation. Our force is equal to minus du over dr. Okay, this gives the relation between two graphs as well. Okay, so this is the relation between force and potential energy. Okay, so by looking those two graphs, we can say that at very low temperature, average kinetic energy of gas molecules is basically very less than lowest possible value of the electrostatics potential energy U naught. So in that scenario, if this is the case, then we can say that the gas condenses into liquid or solid. Okay. So let's talk about the kinetic theory of gas. So those are the basically we call the postulates of these postulate of the kinetic theory of gas. Okay, so these two, 1 and 2, we have only seen this is true for ideal gas. Okay, we have seen before. So we see that there is a very large number of molecules, all identicals, and each having same mass here. Okay, so the concept is we are considering all gas molecules are all identical. Okay, and we also assumed that motion is random and it also has the isotropic, means it could go anywhere. And the other postulate, we would say that the molecules are much smaller than average distance between them, so that the total volume is much less than that of the container. So in this postulate, we assume that if we take this container the container volume is much bigger than the volume of the gas, one molecule. Okay, so if you take the just one molecule, its volume is very, very less than the total volume of the container. So in other words, we can say that there is a very, very small intermolecular force exists between the molecules if this is the ideal gas scenario. Okay, but for the van der Waals gas, we have to consider those factors, and we consider here that the molecules make the perfectly elastic collisions with the walls of the container and with each other. Means in this case we are assuming that there is no energy loss happens in terms of kinetic energy before collision and kinetic energy after collisions is equal. Okay, so will use those postulates to get equations. So our main point here is to find the pressure exerted by gas. Pressure exerted by gas. Okay. Before we actually go on the topic, I just have some notes. Okay, so I'm going to introduce a term. It's called root mean square. Say root mean square velocity. So what does it mean by this? Okay, say for example, I have just three numbers. Say it is 3 meters per second. I have three other velocities, say 5 meters per second. Then other velocities, say for example 6 meters per second. Okay, it could be many, so I just take three. So my goal is how to find root mean square velocity. So you see that root mean square velocity. So at first what I do, I square the velocities. Okay, so 3 squared, 5 squared, 6 squared. So this will include these two square velocities. Okay, this one. Now it's a mean. How do you find the mean then? You are finding the mean of square velocity. So I'm going to add all these. So mean, so we have just three numbers, 1, 2, 3. So I divided by 3. Okay, so now this will include the mean square velocity. See the difference. Okay, now my goal is to find root. So finally I will take the square root. Okay, then now include everything, this whole. So this is called this whole term is called the root mean square velocity. Root mean squared velocity. So, but be careful that average, okay, average is not same as root mean square velocity. You see here, they're different, though the value could be close. Okay, so I'm using this concept to find the pressure exerted by a gas. Okay, say we have, say this is the container. Okay, this is the container. So there may be a lot of molecules over here in the container. These are the gas molecules. So we assume that there is n gas molecules. It could be 100, it could be thousands, or it could be millions. Okay. For simplicity, to make our life easier, at first, for simplicity means to make our math easier. At first, just take one molecule of the gas. Okay. This means we are saying that this container now has just one molecule over here. Okay. So to do some math, we must need the coordinate system. Okay. We need the coordinate system. So I'm just making my coordinate system, say x, y, z axis. And to make this picture more clear, I will draw the other picture. Just like this is the same container. Okay. Just I will make in this form of box. Okay. So let's see. You have to visualize this is x, y, z axis. I'm making a box. Okay. So I'm making a box here. Okay. So you know that I will join this side. I will join this side. I will join this side. Now this is a box. Okay. Same box, same container. Okay. I will assume in the shape of cube of side L. You can take any shape. To make math easier, I just took a cube set. Okay. So maybe then I will take, this is my x-axis, this is my y-axis, and this is my z-axis. Okay. Then I have these molecules, same molecules that I considered before. I have these molecules. Say this phase is x. You know that you have altogether 6 phases. So this is just one phase. That's just I represent by x. So this is just one phase. So altogether we have 6 phases, right? So we can assume, let's start, that this molecule has a speed c. So this molecule has a speed c. So this is the velocity of the molecule. At any time t. Okay. So you know that c could be along any axis. So we can divide this into 3 components. So you know that, say for example, u is the x component of c. I can take v is the y component of c, and g is UV G, UV, I put other symbol so that UV W is the G component. Okay, the G component. Okay, so you know that what is the relation between those UVW and C. Okay, so let's write in terms of vector. Your C vector is, you can write UI. I is the unit vector along x-axis, VJ, and Wk. Okay, so you know that I, j, k are the I, j, and k are unit vectors along x, y, and g axes. So you know c squared, you can write u squared plus v squared plus w squared. Okay, so let's start. Further assume that the molecule which has mass m, because we say that mass is identical to all molecules. The mass of the molecules moves along x-axis only at first. It could be along y-axis only. It could be along g-axis only. Okay, so we can find that if the molecules is only moving along the x-axis, then we can see the picture over here. It will go travel parallel to the x-axis. This means it could go along x-axis with a speed u, and it hits the wall and bounce back with a speed with a velocity minus u, because of your coordinate system. We say that collision is elastic, so uh, speed will not change. Okay. So you can find once it hits the wall, if the molecule hits the wall, we can find the change in momentum. Okay, so in that scenario, you can find change in momentum on impact. Okay, so this is, you know, you can use mu is the initial momentum minus mu. Okay, change means this minus is for change, so you can write it is 2 mu. Okay, then we need to find the time taken by the molecule to move from, say, two walls. One side is this, other side is this. So we have to find the time to go back and forth, going this and coming back. Okay, so you can find the time taken by the molecule to travel from one phase to opposite phase and finally back to initial phase. Means I want to find the time started from this, went to a wall, hits here and come back again. Okay, so we can use the equation. You know that you can use the equations. If you remember, you can use x equals x naught plus v naught times t plus half at square. Based on our coordinate system, this is 0. We don't have acceleration, so this is 0. So you can use only x is equal to v naught times t, this equation. Okay, so based on that, I can write this time will be equal to how much? 2L over U. Okay, so you figure out that time. Next, we have to move forward. Then we can find the pressure. If you know the force, you can find the pressure. So pressure on the face x. Okay, how to find the pressure? So again, I'm going back to the picture. So we want to find, this is the face. Yes. Okay. So the actual picture is this. You have seen again before, just like this face, hitting from one face, starting from one side, hitting the x and come back to the original face. Okay. So pressure is, force per unit area, force per unit area. So you can find, you already figure out force. Force is mu squared over L. This is the force, and area, because this is a cube, so area will be L squared. So we get mu squared over L cubed. Okay. So up to this point, this is just for one molecules. Now we are going back. If n molecules, okay, instead of one molecules, if we have n molecules, what will happen? Each molecule will have different velocities. So C1, C2, C3, so on. Cn are the uh, velocity of molecules number 1 to n at any time. So as before, you see that C1 has altogether 3 components. We say that is U1, P1, W1, XYZ component. Similarly, C2 has again 3 components, U2, P2, W2. Similarly, if you are keep going like this, we can find Cn molecules, the molecule having a speed Cn, it has 3 components. It is Un, Pn, and Wn. Okay. So now, instead of considering just one particle, we are considering the n particles over here. Okay. So let's see here. Okay. So if this is the scenario, then you can find total pressure. Let's find the total pressure. Total pressure on face X. So total pressure means we are considering by n molecules. We are not considering just one molecules, n molecules. So we have to add all those components. Okay. So if you have just one molecules, you have the pressure is mu1 squared over L cubed. If you have second molecule, it will be mu2 squared over L cubed. You have to keep going like this. You have to add all the pressures, mun squared over L cubed. Okay. So this means we can write this as pressure, total pressure P. I write here P equals m over L cubed and un squared plus u2 squared and un squared. Okay. Now at this point, we just consider the motion along x-axis, but we know that we have to consider all the motions along x-axis, along y-axis, and d-axis. Now we have to define root mean square velocities. So how we define that? If you remember, u1 squared, u2 squared, if you keep adding un squared over n that we talked at the very beginning, if you remember that, based on this, this is called the mean square velocities. So this is the mean squared, mean square velocity for x-axis, because we just consider only for the x-axis. Okay, so for symbol we can introduce the symbol. Say this is u squared bar. This is just a symbol. Okay, so I can write this as u1 squared plus u2 squared plus un squared equals n u square bar. Okay, so in terms of this, we can combine this and we can combine that together. We can write P equals m over L cubed. Instead of this, we can write that one. Okay, this is n u squared bar. Okay, in a similar way, we can define other mean square velocities. Okay, similarly, by doing the same approach, we can define u square bar means mean square velocities, v square bar, w square bar. Okay, here is the main point. For random motion of each molecules, we can fairly assume this concept. Okay, I already wrote that, so we can similarly define these terms. Okay, we can fairly assume that u square bar equals v square bar equals w square bar. Okay, so since you know that c squared equals to u squared plus v squared plus w squared, this actually I wrote here, c squared equals u squared plus v squared from our starting point. Okay, let's start and simplify further. So you know that in this equation we can add mean square, c squared u squared bar v squared bar plus w squared bar. We can do that. If this is the case, c squared bar, this is u squared, v squared can be replaced by u squared, and this w squared is also replaced by u square bar. So this means 3 u square bar and c square bar. So this means I can write, based on that, I can say that u square bar is equal to 1 over 3 c square bar. Now I need to plug this value in this part. Okay, so let's combine these two equations. Okay, let's combine these two. What happened this? Okay, let's combine these two equations. Then we find P equals m over L cubed n. In place of u square, I can replace by 1 over 3 c square bar. Okay. Now I just rearrange this m times n over L cubed and 3 here, C square bar. Okay. Now, um, up, what is doing? So just make sure that this m over here is the mass of each molecule. Okay. And this n is the total number of molecules. This means if you multiply m and n, this gives you the total mass. Okay. And L cube is basically the volume of gas. So this means this whole term will give you the mass per unit volume. Okay, so mass per unit volume, this will m times n over L cubed will give you the density of the gas. You can represent by rho. So we got one equation over here, P equals 1 over 3 rho is the density of gas, C squared bar. Okay, so this is the, you know that C squared is the C squared is basically the mean squared. This is the mean square velocity, mean square velocity. Okay. This mean square velocity can be written as this is the C square bar. This can be written as C root mean square velocity square. So these are the same thing, same equations. So just like, for example, you can say 4 is equals to 2 squared. So 4 is mean square velocity and 2 is the root mean square velocity. Okay. So now we can write this equation like P equals 1 over 3 rho root mean square velocities square this. Okay. So basically CRMS means, based on the previous example, CRS means C squared, C2 squared, adding all atoms divided by n and n squared. Okay. If you take only this term without square root, it's called the mean square. Okay. So it depends on textbook. In some textbook, they just use some different symbol. Okay, we can write P equals 1 over 3 rho. They use P squared RMS. So basically, they are the same thing. The concept is similar. Okay, let's move further to explain some of the terms over here after getting the final product. So this is our final product. Okay. Let's use this concept to explain some of the concept of the starting with the temperature. Okay, so now I'm going to enter prediction of temperature based on the theory, on the kinetic theory of gas. So let's start with the equation P equals 1 over 3 rho density P squared RMS. Okay, I can go back and write P equals 1 over 3. This is as before m times n times b RMS square. But be careful about this v and p RMS square. They are not the same thing. So I can write P times v equals 1 over 3 m times n p squared RMS. Okay, I'm just playing with equations. So PV, you know that PV equals nRT for single mole, or for if you take 1 mole, this is PV equals to RT for 1 mole. Okay, so you can write PV equals, PV will be replaced by RT equals 1 over 3 m n p RMS squared. Okay, so in this case, these are the constant. R is constant for all gas. This is the number, this is also constant. This m and n, these are constant for a given amount of gas. But be careful that these two are constant for all gas, but these other are depends on the system, which kind of gas we are taking. Okay, so now based on that, you can say that your temperature is proportional to the P square RMS. P squared means temperature depends on squared values and Vrms squared values. Okay, this also define one of the important concept, that temperature depends on the P squared, not only P. Okay, let's go further and start over here, starting from the same part, this one. Okay, so I will say RT equals, I'm just writing n, I'm just going to rearrange. I'll write 2 n over 3 times half m p RMS squared. I just rearranged that equations. But if you look at here, this will represent what? This is the kinetic energy. This is the kinetic energy of a single molecule. Okay, this is the kinetic energy of a molecule, single molecule. Okay, so you can write 3. I am going to rearrange. So you can see 3 RT over 2n equals half m p RMS squared. Okay, so you know that 3 over 2, this R over n is the Boltzmann constant. So you can replace by KT equals half m p squared RMS. Okay, so you can find that how single kinetic energy of single molecule will depends only on the the temperature. Okay, so this gives you the idea. Let's move further. And so we can find the total energy, total internal energy of gas. So if it has the total number of molecule CGN and multiplied by the kinetic energy of A molecules. So you have N. We have 3/2. We can write K or KBT. So this is the total internal energy of the gas, 3 NkBT/2. Okay, this is also one of the important concepts. So finally, we can say that how we actually going to interpret the temperature. So temperature is average kinetic energy. It depends on temperature. Okay, average kinetic energy. If you remember the heat, it is the total kinetic energy. Okay, so just take one example. You have a bucket. It has a lot of molecules, water molecules. We have a spoon, water. Okay, a spoonful of water. So its temperature is 80 degrees centigrade water. These water molecules. And this is also water molecules. So say its temperature is 35 degrees Celsius. So based on our result, we can say that here average kinetic energy will be low because temperature is lower. Here average kinetic energy will be high because you see temperature is high here. In the other way, you can see here total kinetic energy in this scenario is high because of higher number of atoms or molecules. In this case, the total kinetic energy will be low. Okay, so low because in this case you have the less number of molecules, water molecules. So these examples will tell you that heat and temperature are not the same thing. Say heat, it is the form of energy. Okay, this temperature is not a form of energy, not a form of energy. It only measures the average kinetic energy. This means it measure of degree of hotness or coldness. Measure of hotness or coldness. So I'm just making sure that if you write temperature equals average kinetic energy, this will be wrong. This is just a measure. Okay. So if you understand up to this point, you can solve this practice problem. So what is the average kinetic energy of a gas molecule at room temperature? They give you room temperature, for example, 20 degrees Celsius. And find the RMS speed, root mean square speed of the N2 molecules at this temperature. Okay.